Reach out and touch a star. You cannot, of course, the nearest is more than 4 light-years away, and most are unimaginably farther. And yet we know their temperatures, their sizes, their chemical compositions, their motions and their distances in extraordinary detail. How? Because almost everything we know about the universe beyond our own solar system arrives in a single form. Light, starlight, and the invisible radiation alongside it is the one messenger that crosses the vast emptiness between us and everything else. The physics of that light is therefore the foundational toolkit of all astrophysics, and this chapter builds it from the ground up. We will move from the nature of a single photon, through the glowing spectrum of a hot body, to the sharp spectral lines that fingerprint the elements, to the shifts that betray motion and cosmic expansion, and finally to the ladder of brightness by which we measure the scale of the cosmos itself. Light is an electromagnetic wave, oscillating electric and magnetic fields, propagating through empty space at the speed of light, very nearly 300,000 kilometers every second. Since 1983, that speed has not even been a measured quantity but a defined constant, fixed exactly by international agreement. For any such wave, the wavelength and the frequency are locked together. Their product is always the speed of light, so a long wavelength means a low frequency and a short wavelength a high one. But light is also grainy. Its energy comes in discrete packets called photons, and the energy of each photon is Planck's constant times its frequency equivalently, Planck's constant times the speed of light, divided by the wavelength. Short wavelength light is high-energy light. This single relation, tying wavelength, frequency and energy together, runs through everything that follows. Arrange all the wavelengths in order and you have the electromagnetic spectrum, conventionally carved into bands, radio, microwave, infrared, the thin slice of visible light, ultraviolet, X-rays and gamma rays. The boundaries are matters of convention and overlap, defined more by how each kind of radiation is produced and detected than by any sharp physical line. But the span is staggering, from radio waves meters long to gamma rays smaller than an atomic nucleus. The spectrum covers more than 20 powers of 10 in wavelength. Visible light, the rainbow, our eyes evolved to see, occupies an almost absurdly narrow band in the middle, running only from violet at about 400 nanometers to deep red at around 700. This breadth matters enormously, because different physical conditions shine in different bands. Cold clouds of gas and dust glow faintly in the radio and infrared. The warm surfaces of stars peak in the visible and the near ultraviolet. Gas heated to millions of degrees in supernova remnants and galaxy clusters blazes in X-rays. And the most violent events in the universe, matter swirling into black holes, the cataclysms of gamma-ray bursts, reach into the gamma-ray extreme. To see the universe whole, we must see it in every band, but there is an obstacle. The Earth's atmosphere is opaque to most of the spectrum, letting through cleanly only the visible optical window and a broad radio window, with a few patchy gaps in the infrared. This single fact is the reason for space astronomy. To observe the ultraviolet, most of the infrared, and all of the X-ray and gamma-ray sky, our telescopes must climb above the air, which is why the Hubble, Chandra, Spitzer, and James Webb Space Telescopes were lofted into orbit in the first place. The recognition that light is electromagnetic came from James Clerk Maxwell, whose equations of the 1860s predicted waves of electric and magnetic field that would travel at exactly the measured speed of light, identifying light itself as an electromagnetic phenomenon. Heinrich Hertz generated and detected radio waves in his laboratory in 1887, confirming that they and light were one and the same family. And then the picture deepened. Max Planck in 1900 and Einstein in 1905, with his explanation of the photoelectric effect, the work for which Einstein actually received his Nobel Prize, not his relativity, revealed the particle side of light, the photon. The modern understanding is a duality. Light travels as a wave but delivers its energy as discrete particles, and astrophysics uses whichever picture suits the problem, the wave for diffraction and interference, the photon for counting the clicks of a detector and tracing the transitions of atoms. Begin then with the light a hot object emits simply by virtue of being hot. Physicists idealize this as a blackbody, a perfect absorber that soaks up all the radiation falling upon it and re-emits a spectrum determined by one thing only, its temperature, regardless of what it is made of. This sounds abstract, but it is astonishingly useful because the glowing surfaces of stars, the warm faces of planets, and even the afterglow of the Big Bang all behave, to very good approximation, as blackbodies. Indeed, the cosmic microwave background, the relic radiation of the infant universe, is the most perfect blackbody ever measured anywhere, matching the ideal curve to better than 1 part in 100,000. The exact shape of that glow is given by Planck's law, and its discovery in 1900 cracked the physics of its era wide open. Classical theory had predicted that a hot body should radiate ever more fiercely at shorter and shorter wavelengths without any limit, implying that every warm object ought to blaze with infinite energy in the ultraviolet. This absurd prediction was christened the ultraviolet catastrophe, and it signaled that something in classical physics was deeply, fundamentally wrong. Max Planck resolved it only by making a desperate assumption he scarcely believed, that energy is exchanged with light not smoothly and continuously, but in discrete quanta, in packets proportional to the frequency. His formula fit the observed spectrum perfectly, and in the fitting he had, without quite realizing it, lit the fuse of quantum mechanics. The quantum was forced upon physics by the light of glowing matter. 2 consequences of Planck's law are the everyday workhorses of stellar astronomy, because each isolates a single property of a star. The first is the Stefan-Boltzmann law. The total power radiated by each square meter of a body's surface rises with the 4th power of its temperature. That 4th power is ferocious, double a body's temperature, and it radiates 16 times as much energy. For a whole star treated as a glowing sphere, the total luminosity is its surface area multiplied by its temperature to the 4th power. This one equation binds together a star's 3 most fundamental traits: its radius, its temperature, and its luminosity, and it underlies the entire Hertzsprung-Russell diagram. A vast, cool red giant and a tiny, blazing white dwarf can pour out the very same total light, only because their sizes differ by factors of many thousands. The second consequence is Wien's displacement law, which pins down the color of the glow. The wavelength at which a blackbody shines most brightly is inversely proportional to its temperature. Hotter means bluer, cooler means redder, which is precisely why a scorching O-type star burns blue-white while a cool M-type star smoulders a dull red. Take our own sun, with a surface temperature of about 5,800 degrees. Wien's law places its peak emission at around 500 nanometers, green-blue light, near the very center of the visible band, and remarkably close to the peak sensitivity of the human eye. That is no accident. Our eyes evolved under precisely this sun. From color alone, then, an astronomer can take the temperature of a star that remains a mere unresolved point of light, add a measure of its brightness, and its size falls out as well. But a pure blackbody spectrum is a smooth, featureless curve, and real starlight is not smooth. Spread the light of a star into a spectrum, and you find it crossed by sharp lines, bright or dark slivers at precise, particular wavelengths. These lines are the richest gift that light can give, for they encode composition, temperature, density, pressure, magnetic field, and motion all at once. Their regularities were first codified around 1859 by Gustav Kirchhoff and Robert Bunsen, who discovered that every chemical element emits and absorbs its own unique, unchanging set of wavelengths, a spectral fingerprint as distinctive as any human. 1. Heat sodium in a flame, and it glows a particular yellow. That very same yellow appears dark in the spectrum of the sun, betraying the presence of sodium in the sun's own atmosphere. Kirchhoff summarized the behavior in 3 laws. A hot, dense body or a blackbody gives a smooth, continuous spectrum. A hot, thin gas gives bright emission lines at discrete wavelengths, and a cool, thin gas lying in front of a hotter source gives dark absorption lines at exactly the wavelengths it would otherwise emit. The explanation had to wait for quantum theory. An atom's electrons can occupy only certain discrete energy levels, like rungs on a ladder with no foothold in between. An electron absorbs a photon and leaps upward only if that photon's energy exactly matches the gap between 2 rungs, and it emits a photon of precisely that energy when it falls back down. Discrete energy levels therefore produce discrete spectral lines, and the particular pattern of an element's lines is its unmistakable signature. Hydrogen, the simplest atom and by far the most abundant in the universe, displays this with beautiful clarity. Its visible lines follow a strikingly simple mathematical pattern, discovered by Johann Balmer in 1885 and generalized by Johannes Rydberg. The wavelengths are governed by the differences between the reciprocals of 2 whole numbers, nothing more. In 1913, Niels Bohr explained why, by daring to suppose that an electron's orbit could take only certain quantized sizes, and deriving the formula and the constant within it from first principles. Hydrogen's visible lines make up what is called the Balmer series, and its first and strongest member, known as H-alpha, is a deep red line at 656 nanometers. It is this line, glowing from vast clouds of hydrogen lit by the hot young stars within them, that gives the great emission nebulae their characteristic rose-red color in astronomical photographs. Because the strength of each line depends on temperature, a star's spectrum can be read as a thermometer, and this insight built the very system by which we classify the stars. The work was done at Harvard College Observatory between roughly 1885 and 1924, above all by Annie Jump Cannon, who personally classified several 100,000 stellar spectra by eye, at a speed no one has ever matched. She reordered the older, muddled alphabetical scheme into a clean sequence of falling temperature, and the result is the great stellar sequence still used today. OBAFGKM, running from the hottest blue stars down to the coolest red ones, and famously fixed in memory by the phrase "Oh, be a fine guy, kiss me." Our own sun, a middling yellow star, sits comfortably in class G. One deep puzzle remained, though, that mere classification could not itself solve. Hydrogen is overwhelmingly the most abundant element in every star, and yet its lines are weak in the hottest stars and weak in the coolest, peaking only in the intermediate white A-type stars. Why should the commonest element in the cosmos hide where stars are hottest and where they are coolest? The answer came from the Indian physicist Meghnad Saha around 1920. His equation describes how a gas ionizes as it heats, how its atoms are stripped of their electrons. In the hottest stars, Saha showed, hydrogen loses its electron entirely and cannot make the visible lines at all. In the coolest, its electrons sit too low to absorb visible light, and only in between is the balance just right. Saha's insight that a line's strength reflects the temperature-driven populations of atomic states, and not merely how much of an element is present, turned stellar classification from cataloguing into genuine physics, and ultimately revealed that the stars are made overwhelmingly of hydrogen and helium. Light carries not only the identity of the atoms that made it but their motion. When a source of waves moves toward us or away, the observed wavelength shifts, the Doppler effect, the same phenomenon that drops the pitch of a passing siren. In astronomy, it turns every spectral line into a speedometer. Compare a line's observed wavelength with its known rest wavelength, and the fractional shift reveals the source's velocity straight along our line of sight. A shift toward the red, toward longer wavelengths, means the source is receding. A shift toward the blue means it is approaching. For ordinary speeds, the relation is beautifully simple. The fractional shift in wavelength just equals the velocity as a fraction of the speed of light. Modern spectrographs measure this so exquisitely that they can detect a star wobbling at the pace of a walking human being, about 1 meter per second. That precision opened up an entire field, the hunt for planets beyond the solar system. An unseen planet does not merely orbit its star. The two swing about their common center of gravity, so the star traces a small, answering circle, lurching very slightly toward us and away as the planet goes round. That rhythmic lurch shows up as a periodic Doppler shift in the star's spectral lines, and from its rhythm we can read off the planet's orbital period and estimate its mass without ever seeing the planet at all. Jupiter tugs our own sun to and fro at about 12 meters per second. The Earth manages a mere 9 centimeters per second, right at the edge of what today's finest instruments can sense. It was by exactly this method that the first planet orbiting a sun-like star, 51 Pegasi b, was found in 1995, a discovery honored with the Nobel Prize in Physics in 2019. At very high speeds, the simple Doppler formula must be corrected, because Einstein's relativity folds the slowing of moving clocks into the reckoning. And here, a warning sign appears. If one naively multiplies the redshift by the speed of light to get a velocity, then for a redshift greater than 1, as it is for the most distant galaxies and quasars, the answer comes out greater than the speed of light itself. That is impossible for any genuine motion through space, and it is a clear signal that, at cosmological distances, we are no longer dealing with ordinary motion at all, for there are two quite different things that both go by the name redshift, and confusing them is one of the classic errors in all of astronomy. A true Doppler shift comes from a source's real motion through space at the moment it emits its light, but a cosmological redshift comes from something far stranger, the expansion of space itself while the light is in transit. As the universe swells over the millions or billions of years the photon travels, the very wavelength of that photon is stretched along with space. The measured redshift then tells us not how fast the source was moving, but simply how much the universe has expanded since the light first set out. A galaxy seen at a redshift of 7 emitted its light when the whole cosmos was 1/8 of its present size. And because this stretching reflects the growth of space rather than a velocity through it, it is under no obligation whatever to stay below the speed of light. The last piece of the toolkit is the measurement of brightness itself, and astronomy carries its scale down, remarkably, from antiquity. The Greek astronomer Hipparchus, more than 2,000 years ago, sorted the naked eye stars into 6 magnitudes, calling the brightest first magnitude and the faintest he could see sixth. The scale is therefore backwards. Smaller numbers mean brighter stars, and because the eye responds to light roughly logarithmically, it is also approximately a logarithmic scale. In 1856, Norman Pogson tied this ancient ranking to precise measurement, noting that a first magnitude star is about 100 times brighter than a sixth. He fixed the step so that 5 magnitudes correspond to exactly a 100-fold change in brightness, making each single magnitude a factor of about 2.5. The scale spans an astonishing range. The Sun blazes at magnitude -27, the full moon at about -13, Sirius, the brightest of the night stars, at -1.5, the faintest star a sharp eye can catch under a dark sky sits at about +6, and the deepest telescopic exposures reach past magnitude 30. The Sun outshines Sirius by some 25 magnitudes, a factor of 10 billion in actual brightness, all captured within that compact little span of numbers. And the difference between a star's brightness measured through 2 different color filters, its color index, is itself a distance-independent thermometer, for it samples the slope of the blackbody curve. A blue star and a red star wear their temperatures openly in their colors, but how bright a star looks confounds 2 entirely separate things: how much light it truly pours out, and how far away it happens to lie. To disentangle them, astronomers define the absolute magnitude, the brightness a star would appear to have if it were placed at a standard distance of 10 parsecs. Absolute magnitude is thus a pure measure of intrinsic power, stripped of the mere accident of distance. The parsec itself, that fundamental cosmic yardstick, is the distance at which the radius of the Earth's orbit would subtend an angle of just 1 second of arc, a little over 3¼ light years. The bridge between how bright a star looks and how far away it lies is the inverse square law. Light spreads outward from its source over an ever-growing sphere, whose area climbs with the square of the distance, so the brightness we receive falls off with the square of the distance. Move a star twice as far away, and it appears 4 times fainter. Combine this simple geometry with the magnitude scale and you obtain the distance modulus. The gap between a star's apparent and its absolute magnitude widens by 5 for every 100-fold increase in its distance. So if you know a star's true luminosity and you measure how bright it merely appears, the difference between the two tells you exactly how far away it must be. Find an object whose intrinsic brightness you already know, and it becomes a milepost planted in space. Such objects are called standard candles, and by chaining them together, astronomers build the cosmic distance ladder that measures the universe. The lowest rung is pure geometry, the tiny parallax wobble of nearby stars against the far background as the Earth swings around the Sun, now measured for well over 1 billion stars by the Gaia spacecraft. That calibrates the next rung up, the Cepheid variable stars, whose steady pulsation period betrays their true brightness through a law discovered by Henrietta Leavitt. The Cepheids in turn calibrate the brightest candles of all, the type Ia supernova, whose nearly uniform peak brilliance lets them be seen across billions of light-years. Each rung is built upon the one below it, carrying our measuring rod ever deeper into the cosmos, and at the very top of the ladder lies one of the sharpest mysteries in physics today. Measuring the distances and recession speeds of far-off galaxies yields a value for the expansion rate of the universe, the Hubble constant, of about 73. Yet a completely independent method, reading the same constant from the faint afterglow of the Big Bang and interpreting it through our standard model of cosmology, yields about 67. The two disagree far beyond their stated uncertainties, a gulf now known as the Hubble tension. It is a live and unresolved debate, not a settled fact. Recent observations from the James Webb Telescope have largely ruled out simple errors in the Cepheid measurements, leaving open the tantalizing possibility that the discrepancy is pointing us toward genuinely new physics. And the entire question rests upon the chain of reasoning built in this very chapter, from a photon's energy, to a star's temperature, to its luminosity, to its magnitude to its distance. That chain is the through line of the whole subject. Nearly everything we know of the universe, beyond our own small corner, has been decoded from light, read out of the pale, faint beam of a distant star, from the two simple relations that tie together a photon's wavelength, frequency, and energy, through the blackbody laws that let us weigh a star's heat and its size from its glow alone, through the spectral lines that name its elements and clock its motion, through the Doppler shift that weighs unseen planets and charts the expansion of space, to the ladder of brightness that measures the very scale of the cosmos. It is all of it written in light. The stars themselves remain forever beyond our reach, but their light reaches us, and in learning patiently to read it, we have learned to read the universe.